speakers, seminars, and tutorials on various topics to equip you with some useful quantum computing tools. For today's session, I am excited to introduce Dr. Zlatko Minev, who will be giving an introduction to superconducting qubits. Dr. Minev received his PhD in applied physics from Yale University, working in the Devorey Quantum Lab. At IBM Quantum, he is a research scientist whose work focuses around studying quantum predictability and randomness, scalable hardware architectures for quantum computers, and design of superconducting quantum circuits. In addition, he leads a quantum computing design and software team, which is now known as Qiskit Metal. He was also featured as a visionary in the MIT Technology Review 35/35 for his work. Please welcome him.
Thank you very much for the kind introduction. I hope you can hear me just fine.
Yes, we can hear you.
All right, wonderful. Well, I think the pleasure here is really mine to have the chance to virtually zoom in over and across oceans and be with you today. I am thrilled to share this lecture, and I want to thank you also for your time here. Feel free to post questions in the chat, and I think you will get to them. And I'll pause every once in a while to take a couple of questions. So,
Dr. Minev, I would like to welcome you on behalf of QIQT. I'm Prashant Panigrahi, the convener of this workshop.
It's a joy to be here, and thank you very much.
Thank you.
Lovely. All right, so I thought we would begin with the questions that this lecture will answer today, which is, what is a real qubit? The kind of superconducting qubit you might have logged into the cloud and used already. And even more importantly, or more especially, how can you actually design, control, and measure a real qubit, as well as how can you understand what happens and goes on underneath the physics of these qubits, and perhaps even make your own quantum computer. And the reason that you might want to do all of this and focus on these questions is that they are valuable and practical stepping stones needed in your career in quantum to be successful. And I think the next hour will give you those skills needed to grow in the field, and Thomas will take you one stage and one step further. Now, on our road ahead, on the journey we have today, we'll begin with the picture of qubit in the cloud and what that means and looks like. And the building stepping stones for that will be the core ideas of how you can create a qubit, a two-level system, from a physical real system that has many levels. One of the theses of this talk is that there is no such thing as a qubit or a two-level system. There's always more levels and more degrees of freedom. Then we'll dig into the bread and butter core building block of all qubits, and that's the transmon, so-called transmon qubit, which is very close to a harmonic oscillator. And so in order to also build up to that, we'll review the classical resonant LC circuit or harmonic oscillator, as well as the quantum version of that, zooming from classical to quantum, and finally digging deeper at the actual mathematics and physics of the transmon qubit, which is what Thomas will show you how to practically do by using Qiskit Metal in the second half of this talk. So this first half is more on the foundations. Today is an introductory lecture, and if you've already seen some of this material, I think of it as skill reaffirming. You don't necessarily need too much going in, but we will cut quickly far and deep, trading scope for depth. But I think this will give you all the principles you need to then venture out into dangerous bends and more advanced material on your own. We'll start with the simplest, most practical examples, as much as possible, step by step. So feel free to ask questions. Try to answer each other's questions if you can as well. And we'll try to get to as many of the questions as we can. You can always ping me on Twitter, and we can try to take that off there. Thomas will follow up in the second half here as well. Let's begin with one of my favorite quotes in quantum physics, which is that there is no such thing as a Hilbert space. There's only a laboratory, as Asher Paris put it much more eloquently here in this quote. In the spirit of this quote, the rest of this talk will be starting with qubit, idea to reality, starting with the big picture before we dig into exact precise calculations. What is the idea of a qubit? A qubit stands for the smallest, simplest quantum system, the bit, the binary system, which has two energy levels, the 0 energy level and the 1 energy level, which you can see here as the 0 and the 1 depicted with these Dirac bracket notation. And that's how we typically think of the qubit in an abstract way. Those two levels also give rise to something we call the Hilbert space, essentially the space of computation, the space in which your state or wave function lives, typically drawn in the Bloch sphere, like this, living on the edges of the Bloch sphere. But all of these are more or less tools of the mind that we use that represent physical real structures that live in the laboratory, or maybe nowadays in the quantum cloud, here depicted like this. We're going to take some of this abstraction away and dig underneath to see how these things actually arise. There is no cloud, of course. It's somebody's computer, or somebody's lab, or somebody's lab fridge. So you might have used your laptop to log into the cloud and execute different kinds of quantum operations, such as this Hadamard gate, S-gate, T-gate, a general unitary on a single qubit or multi-qubit. But how does this actually work? Well, let's start with something near dear and familiar to all of you here, which is, of course, the laptop that you're logging in from today. That in of itself can then communicate with this lab cloud facility. Here's a picture of one of the ones from back here home at IBM Quantum. Within that facility, you notice these hanging fridges. If you unsheet the fridge and remove all the shields, you'll find a cryogenic environment. This is a dilution refrigerator, the golden chandelier that you see depicted. It's literally covered in gold. And you see a bunch of input-output wiring that takes signals in and out of the fridge. These are microwave signals. And at the very bottom here, you see a little canister. This canister is a shield that itself houses the only quantum part of this whole picture. And that is the quantum device chip. Everything else is just classical input-output routing and details that we don't need to worry about too much, because the real brain, the heart, the beating neuron of the quantum processing devices is the quantum chip. This is such a beautiful picture, I couldn't resist to show you a zoom in of what the golden chandelier looks like in practice, but we'll only focus on what happens down here and take a look at that by zooming right into it at a picture of a quantum chip from a few years ago here from IBM Quantum, where you see that we have an optical image of a chip that has a substrate. This is typically silicon or sapphire, something like that. And there's a number of structures on top. These are all metallic structures placed on top, and we'll go over what these structures are. You see that these little two rectangles connected by a line are qubits. All the squiggly lines on the edges are resonators, essentially wires that have boundary conditions that set up resonances that oscillate. And one of these structures here, this qubit coupled to this resonator, is a really primitive building block of the entire field of circuit quantum electrodynamics, which is what our superconducting qubits in the cloud actually come from. So one way to view this is to zoom into this structure, which you see almost stamped and repeated over and over again on the chip, and to look at the connection to the abstractions we saw earlier, such as this Hilbert space of the qubit. Well, that Hilbert space represents actually something that's associated with and happening with this structure here. We call this the transmon qubit. It's almost the simplest thing you could see or think of. You notice that there's kind of two metal pads which I'm shading in here. And then there's this white line. This will be a special element called a Josephson tunnel junction that we'll introduce in this lecture. But for the most part, you can think of this entire circuit here as a capacitance coupled to this nonlinear inductor, this Josephson tunnel junction. That's the circuit here on the left. And on the right, this entire squiggly, meandering, so-called coplanar waveguide that Thomas will talk a lot about in the following lecture can be seen simply as a resonator, probably familiar from your high school as a LC circuit. These circuits, while having a first pass of a classical view, can be more deeply understood at the level of quantum physics by algebra and operators that look like this, raising and lowering operators that we'll touch on and introduce and refresh for you in the second part of this lecture. So this is where we're going to be headed. We're going to peel away all these elements in primitive building blocks, starting with the oscillator, then moving to the transmon qubit, which you notice looks almost the same, except that the inductor part has been replaced here by Josephson tunnel junction. But let's also zoom out and show you the overall design flow. This is the design flow that also we've now had the pleasure to automate in Qiskit Metal with the software team that was mentioned. Starting with the transmon qubit depicted here on the bottom left, each piece of metal has electrons. Electrons can move. They can move across from one metal to the other, but the only way they can do that is through the little drawbridge that sits in the middle, the junction. As a first pass at understanding the physical layout that you see in that picture is to do a standard electromagnetic analysis, something you might have studied or touched on, and really to view these structures as nothing but an ordinary microwave oven in your kitchen. I think I have one right here behind me. To first pass, these structures are microwave oscillators, just like that object behind me, that oscillate in more or less even a similar range of frequencies between 1 to 10 gigahertz and have electromagnetic fields and so forth, charges moving and flowing, more familiar notions. But that's only a first pass. Quantum departs from classical at the next stage when we actually have to understand the quantum properties of these objects. The object behind me, this microwave, doesn't have this quantum notion able to expose itself, but superconducting devices we'll look at do. So we have to then be able to bridge this classical to quantum gap and really understand then the quantum behavior of these objects. From this larger Hilbert space, from this larger many energy levels and so forth, we'll find and reduce into a small 2-qubit space of a qubit. And that's what we'll use at the end of the day for our logical computation. And finally, in the design here, we always have to iterate because you can never get things right the first time. This is a common lesson in science. You have to start at the physical layout, go to the electromagnetic analysis, then the quantum, then find your Hilbert space. Then you find out that you weren't quite where you hoped to be in terms of the properties of the qubit. You then have to iterate back in the physical layout, change some of the parameters, maybe change the width of this rectangle and so forth, and that will somehow affect what's happening at the level of quantum. And it's making that tight link between the two that we want to really begin to automate and understand, because that's really where the departure from the classical engineering of systems is to that of quantum. I love this cartoon, which shows us the bridge from classical devices over this barrier, which is what we're going to hop over today, into the world of quantum, where you have Schrodinger cats and things that can be in two places at the same time, or dead and alive, as kind of depicted here in this figure. Overall, I think it's incredible that we have such a tight link at the level of 10 to the minus 5, even with the newer methods, between the physical hardware and these abstractions of the Hamiltonian. It's a miracle. I really think it's a miracle. And this was not obvious at all, even as far back as 10, 20 years ago. within the last 6 months, we've now also released this software called Qiskit Quantum Device Design, or just Qiskit Metal because it talks about the metal on the chip, that allows you to go from a device that's laid out, such as this 5-qubit device here that we made at IBM, into the actual description of that device, the Hamiltonian, its wave functions, as well as maybe the conductivity of the graph and so forth, and iterate back and forth, and to begin to automate as much of the process and the details of what we'll talk about today. But you need to understand sort of the core ideas we'll cover today in order to be able to really make the best use of this. So let's begin with the core idea of how we go from a qubit to reality. And I thought I would start with the bright light of atoms. I think all of you have seen fireworks just a few days ago here. It was July 4th, so we saw quite a few of them. The different colors of the fireworks are associated with different atoms because each of the atoms has a different spectrum that it emits at when the atom is excited by the explosion. And those colors are associated with discrete energy levels of the atoms. For an electron around a nucleus, you might have an energy potential landscape that looks something like this, where you can expect the electron to have very low energy when it's very close to the atom here, and it takes more energy to be further away from the atom here. This is the distance from the nucleus, and this is the energy on this axis. Classically, the particle can be anywhere on that hill. Quantum mechanically, however, the energy you measure can only ever be found in discrete elements, in discrete lumps at discrete stages, which is the reason that you see the colors in the fireworks. And so here you see that we have a number of different lines. Each line represents a different energy level that the atom can take. This is a so-called anharmonic degree of freedom. Anharmonic because you notice that the spacing between the different levels is different. And so if you try to apply a force to the atom to move it from one energy level to the other, you're not able to continue up the ladder of levels, but you can isolate at a particular frequency of, say, a laser. You can isolate specifically two levels, such as the 0 and 1, because the frequency of this laser will exactly be resonant with those two levels. That's a core idea that allows you to isolate from this large Hilbert space of many, many levels, just two levels, our logical 0 and logical 1. And this kind of level diagram allows for qubit-specific control and readout. That will be an idea that translates across superconducting qubits, atoms, ions, NV center, all the kind of different platforms you may have heard about. It's also important for this atom to be fairly well isolated from the environment and the thermal fluctuations. That's one reason that atoms are quite nice sometimes, because of course, if you have some noise that's going to come in here and jiggle the atom about, well, that jiggling is going to throw off your calculation. And in that sense, the atoms are low lost, and there's always more than two levels. You see here, we can realize our qubit from a multi-level system of the atom that has the right structure to allow us to restrict ourselves to the lowest two levels. What we'll do in the rest of the lecture, however, is not play with real atoms, which come in a variety that's fixed. Rather, we will take a composition of electrical elements in order to create an artificial atom. Artificial in the sense that it will mimic the electromagnetic properties of real atoms, but is one that we can engineer all the actual specifics of, such as this really nice LC oscillator here. So this is a capacitor on the left and an inductor on the right. Let's compare now between the two. And let's see if my slide will advance here. There we go. And this is a capacitor and inductor. And just like the atom on the left, we see that the harmonic oscillator on the right has a potential energy that looks something like this quadratic function. Classically, for an oscillator, the particle can climb up this hill anywhere, but quantum mechanically, the energy of the oscillator can only be found in discrete lumps, in discrete units, typically here of h bar omega, the frequency of the oscillator. If we couple that oscillator to the outside world, here depicted as a little wire that electromagnetic waves can travel and can bounce back and forth from, then we can also use, just like the laser, the light that we shine in the microwave world here, to try to control this oscillator. But you notice now that if the atom starts in the very ground state and we shine the laser at some frequency omega, it will take us to the first excited state. But as soon as we're there, then the first excited state is resonant with the second excited state and the third and so forth. So we no longer have that ability to isolate the levels on the left. That's why we're going to introduce a nonlinear element called the Josephson tunnel junction, which will taper the potential, make it open up, and that will create an anharmonicity so that the energy difference to go up a little bit further, the further you climb, gets smaller and smaller. It's easier and easier to climb the hill as the hill gets less and less steep. And that's what you see here on this picture. And that will create an anharmonicity, meaning that the levels are not equally spaced. And that anharmonicity will allow us to then isolate just the lowest two levels in the structure to use as our qubit. That's essentially the whole idea behind the rest of what we're going to see, to go between the physical layout into an electrical circuit model that looks classical to first degree, but then we need to bridge this classical to quantum gap and understand the anharmonic system. Then we shape its spectrum and isolate the lowest two levels to finally create our perfect, near perfect qubits. And the rest of the focus is on the middle two elements today. And this field has a name. It's called circuit quantum electrodynamics. Electrodynamics because it has to do with the dynamics of electric and magnetic fields or circuits. Quantum for obvious reasons, and circuits because that's one way to understand this. The other way to understand the world in which you live as a physicist or a scientist or a quantum aspiring scientist is that there's two kinds of physicists: those who believe all of physics is spins and those who believe all of physics is oscillators. I ask you, which one are you? Feel free, by the way, to type that in the chat if you feel strongly about this. The ingredients of this field are microwave oscillators, which we saw in the picture earlier, and the following circuit elements: capacitors, inductors, this nonlinear junction element that we'll introduce, as well as these input-output transmission lines, or just wires that we use to send information around. However, you can take these four building blocks and use them in an infinite number of ways in order to create essentially all the different pieces that we would want to see. Here I've depicted a few different examples of a resonator, a transmon qubit coupled to an oscillator with an input-output. Essentially, by putting these ingredients together, we're going to create a great variety, and it's really important to understand these few building blocks. You might ask, well, if these are all electrical elements, then how come my microwave oven isn't quantum? Well, there's a few reasons for that. First of all, to see quantum behavior, you generally need very small dissipation, low loss. Your microwave oven is not low loss. It has quite a low Q, a quality factor. It needs to be isolated from the environment. Well, sitting in the kitchen doesn't help. It has to be a very low temperature. It's 90 degrees Fahrenheit here. It has to have some nonlinearity so that we can break away from this degeneracy of the level transitions. doesn't really have that either. It's quite a linear system in many ways, and it needs to usually have very large zero-point quantum fluctuations. That means that in quantum, nothing is ever at rest, even when you're in the lowest allowed energy state. That's why we have this usually 1/2 h-bar omega for a resonator. Even then, on average, the position of a particle may be zero, but if at any instance you look at it, you won't find it at zero. It's fluctuating, it's jiggling about and fluctuating. And the size of those fluctuations typically needs to be large in our quantum circuits, as that will dictate the amount of nonlinearity and interactions between the two. And this is why superconductivity is so useful and important, because normally it gives us zero intrinsic dissipation and heat. The nominal temperature of the bath is far below the energy level splittings of the oscillator. And finally, there's this miraculous and very robust effect called the Josephson tunnel effect, for which Brian Josephson, depicted here on the right, received the Nobel Prize, which provides that low loss, near dissipationless nonlinearity, and that's given by this element. I think it's instructive to also put some of these abstractions in perspective. There's a little image here that should be showing up, but unfortunately it doesn't seem to be. So you'll have to take my word for it. Essentially, we have the wavelength scale, frequency, and effective temperature of things you might see in your daily life. Over here on the left, we'll have radio frequencies. These have typically a wavelength of something like 10 to the 3, and sort of the size of this is buildings. Then we have humans over here. We'll just draw humans like this. Then we have smaller and smaller objects, such as butterflies. This is going to be my butterfly symbol, so you can really see how great of an artist I am here. Then at the infrared level, we'll have things like a needle point. And then we have visible range, where we have things like microbes. So I'll just kind of draw my microbe structure a bit like this. In the ultraviolet, all the way down here, we have molecules. At the level of X-rays, we now have atoms, and so on. The range in which our story unfolds and takes place for the level of optical real atoms is over here. This is sort of at the level of, let's say, roughly 10,000 Kelvin, which is very, very hot, roughly 10,000 degrees Celsius, kind of at the level. This is where your red, green, and blue visual range of frequencies is. We're going to operate instead at the level of sub 1 Kelvin, or negative 272 degrees Celsius. That's where our LC circuits will live, inside of this cryogenic dilution refrigerator, which will have a temperature of about 10 to the minus 2 Kelvin. So the length scales here are somewhere between a butterfly and human at the level of 10 to 30 centimeters. These are a few introductory reviews that you can take a screenshot of if you want more depth on some of these subjects. Instead, we're going to directly press forward and dive right into the field of circuit quantum electrodynamics. And as I've alluded to, in order to do quantum, you may as well begin with classical. And there's no better classical systems to start with than that of the oscillator and the transmon qubit. But we'll see the transmon qubit by an approximation here as an oscillator first. This is a picture of an actual physical device in the quantum systems. And in this device, we see that there's going to be kind of two metal pads. This is metal in this side. This is also metal on this side. Just aluminum or niobium, doesn't really matter. The black region you see here there's no metal. That's the substrate behind it, let's say silicon, and then there's this white line here that will be the Josephson tunnel junction. So if I give you a nice 3D kind of isometric view of this, we see the same structure where we have the substrate dielectric, the two metal pads, as well as an inductor connecting the two, here just depicted by that orange box. How do we understand what actually happens here? Well, you can think of this as charges on the two islands, plus and minus charges. On one side, we have a net positive charge. On the other side, we might have a net negative charge. The number of charges that are actually mobile, that are going to move in one of these islands, is typically on the order of 10 to the 12 mobile electrons. And the amount of net charge we can denote by the variable q, plus q and minus q of t. It's a function of time, and is a number that goes between minus infinity and plus infinity. The charge is going to set up an electric field between the two, denoted here by the vector E as a function of position r and time t. We don't need the details here, I'm just illustrating the larger picture. And that electric field will sort of uniformly point from one side of the pads to the other side of the pads. As with any electric field, we can define a voltage. Here I've denoted the voltage by V of t, and it's the following integral expression. It just says, well, what's the net potential drop from one side of the island to the other, and we'll probably just take the two edges here. And voltage is, again, a quantity from minus infinity to plus infinity. Once we have the notion of charge and voltage, we can set up the idea of a capacitance, the capacitance between these two metal pads, which is just the relationship given by the geometry in the fields between the voltage drop across the two capacitors and the amount of charge on each of them. Capacitance is itself a quantity that goes between 0 and infinity and is symbolically denoted by the following symbol. Once you have charge, you can also have the movement of charge, which we describe as current. So here I've shown that one of the charges has decided to travel across the bridge, the inductor, and we can now talk about the rate of charges moving across that drawbridge. We'll call that the current, or I of t. And so the rate of change of charge is equal to the current. This is a universal relationship independent of the nature of the individual elements, and it's a statement of conservation of charge. And so equally, if you integrate this equation and assume the initial charge is 0, then you can find that charge is the integral of current. The initial conditions we've assumed is that everything is at rest. There's no net initial charge. Current goes from minus infinity to plus infinity. And for the more subtle and experts in the audience, we can point out that we're going to assume a particular convention. This isn't always the convention, but this is called the passive sign convention. This is going to be useful for setting up the energies later, that the voltage and current are defined opposite, meaning that we say positive current flows down and positive voltage goes up like this for branch B. This is only half of Maxwell's equations. The other half has to do with what current leads to. The flow of current will in itself lead to the buildup of magnetic fields and therefore magnetic flux. So if you see these lines here depicting essentially the magnetic field, you can associate them with magnetic flux denoted by a capital phi. For a kinetic conductor such as a Josephson tunnel junction, there's maybe a little caveat here that most of the actual inductance and flux isn't going to be in the magnetic fields, it'll be in something else because of superconductivity. Just keep that in mind as an asterisk, but we don't need to worry about it too much. For the purposes here, especially of a linear inductor, you can think of this as the magnetic flux. And there's a very nice and simple relationship between the voltage between the two terminals of this device and the total flux, which is given by Faraday's law of induction. This is a universal relationship, and it tells us the integral of the voltage from the initial time, which here we'll denote as minus infinity to time t, is equal to the total magnetic flux. Just like charge, you see that there's a duality between charge and flux. For charge, we had Q and we had I here. It's the same expression otherwise. And similarly, the rate of change of flux is equal to the voltage. And for charge, we had Q and I. So note the duality between the two. Flux, just like charge, is a variable from -infinity to infinity. And the relationship between flux and current is just like the relationship between charge and voltage, related by, rather than a capacitance here, an inductance. And that inductance goes from 0 to infinity. It tells us about the resistance to the flow of current. And that inductance we symbolically depict in the following way. A very key and important concept is that of power and of energy. We can define the amount of power that's going or flowing through one of these elements, such as the capacitor on the left or the inductor on the right, as the rate of change of energy, which is equal to P of t, the power at time t. This is going to be understood as the instantaneous power flowing to the component, as opposed to out of the component. And that's defined as, or equal to, the voltage of the component times the current of that component. So for instance, we might have V of t like this and I of t like this. Then clearly the energy is just the integral of the power. Using this expression and substituting in here V of t, I of t, and using the relationships again that phi is equal to Li and Q is equal to CV, you can from here derive the following two expressions, which is that the energy of a capacitor is a function of the voltage. Remember that the rate of change of flux is equal to just the voltage. So it's 1/2 C phi dot squared. The phi dot denotes the time derivative of phi. Maybe just to be explicit, phi dot equals d dt on phi. And then the energy of the inductor as a function of the flux is equal to the amount of flux squared divided by 2 times the inductance L of this inductor. So this has an L and this has a C. Alternatively, if you wanted to, you could also just as well write each of these as a function of not the flux across the element. We can define this again here as a flux phi, but each of these elements can also be associated with the charge Q. And so you can equally write these expressions, but we won't really need those two. Rather, what we can leverage and use is a mapping, a reduction between this more complicated object that has geometry and materials and so on, and the structure on the right, which tells us about a simplified model of what this qubit will look like to first order. And to first order, we're going to treat it as simply an inductor and a capacitor in parallel. The capacitance value of this capacitor is C, that of the inductor here is L. This is my symbol for a node of the circuit, and this is just a reference point denoted as the ground. For those of you who come from more of an electrical background, I'll remind you of Kirchhoff's laws. Won't really need most of this for the rest of this talk, but there's essentially 2 ideas: that of conservation of charge, that on any node, such as this node here, I'll denote it as B, the sum of the charges of the elements, so maybe the charge in the capacitor and the charge due to the inductor, is equal to 0 with the right signs in place. So if we kind of write out the rules of Kirchhoff for this particular circuit, we'll see that the charge on the capacitor plus the charge on the inductor is equal to 0. That's just Kirchhoff's law at this node N1. So this is our node B. B here equals N1, the first node. And the dual of the conservation of charge is Faraday's law of induction, or Kirchhoff's voltage law, which says that the sum of the voltages around any loop, and there's only one loop here, given by this brown arrow, is equal to 0. And so for the first loop here, the voltage on the capacitor minus the voltage on the inductor, if you'd like, you can write it like this, is equal to 0. So you can eliminate one of the two, and we can find out that the voltage on the capacitor is equal to the voltage on the inductor, which we know well. Now, taking both of these equations together and eliminating the charge using the constitutive relationships again that Q is CV and this is we can write maybe instead as phi C dot, and this is the charge on the capacitor, and here we have also the flux on the inductor is equal to the inductance times the current, which is QC dot. Taking these three relationships together, we can find out our standard harmonic oscillator equation, that the capacitance times the voltage second time derivative plus L inverse times phi is equal to 0. So this is an oscillator with the following, this will give oscillations as the solutions, with the following solutions. If you essentially rewrite the above equation by finding that the frequency of this oscillator is 1 over the square root of LC, you'll find that we have the following equation. That's the resonance frequency. And one way you can make an analogy of this is to think of the magnetic flux phi as the position of a spring that's of a mass suspended from a spring from a ceiling, shown here. And the flux phi of t gives us the deviations away from equilibrium. And what this classical oscillator will do in time is just oscillate up and down like this in a harmonic motion. Phi dot is then analogous to the velocity of a classical particle. So this is the analogy between a mechanical and a electrical oscillator going from flux to position, and in that case the charge, the capacitance looks like the mass, the momentum of the classical particle P looks like the charge of the circuit. The spring constant K of the classical oscillator looks like the inverse inductance. So we can use that to write down the Hamiltonian, just like the quantum Hamiltonian, but this is now right now for a classical particle. The Hamiltonian, the amount of energy of the system, is a function of the flux and charge of that circuit. This is the flux, which tells us about the voltage, and this is the total charge stored in the capacitor, and is equal to the energy of the capacitors, which is Q squared over 2C, plus the energy of the inductor, which is pi squared over 2L. The resonant frequency is omega squared is equal to 1 over LC, and then the impedance, which tells us about how this structure responds to an external drive, is equal to the this is Z0 squared is equal to L over C. If we now put a picture to some of these words, we can think of this as the potential of the particle, which is phi squared over 2L. And so a classical oscillator is bound to live somewhere on this hill, and is a bit like a ball rolling up and down this hill. And its capacitive energy is going to tell us about the momentum that looks like this. I think it's important to have these pictures in mind because, as Henri Poincaré said, it is by logic that we prove, but it's by intuition that we discover. And so one other way to think of this, if you want, in the momentum space, is to look at position, which is like flux, and charge, which is like momentum. This is again of the classical particle, which we'll use to bridge into the quantum world. And for a given energy, this particle has to live and has to oscillate on one of these circles here like this. Each of these circles gives us a different energy, such as h bar omega naught over 2. Now, I haven't told you right now why I've chosen Planck's constant h bar and put it in here, but suppose that I do the semi-classical approach where I say that the energy of this classical oscillator suddenly somehow, for some reason, quantized in units of h bar omega, omega being the resonant frequency of this oscillator. And each of these lines here gives you the trajectory that this classical particle will take. So the lowest line here corresponds to an energy of h bar omega naught over 2. The next one is 3 h bar omega naught over 2, and so on. So suppose that we have the particle starting out not in the lowest state, which later we can associate with the zero state, but in the first excited state. Now, we haven't shown that these are semi-classical approximations, but let me give you some intuition as to what will happen in the quantum world. Well, in this case, what the time evolution of the particle will do is given by the way that the voltage will oscillate in time and the way that the charge will oscillate in time. So this is the voltage and this is the current. And there are expressions given by the partial derivatives in the Hamiltonian. So the way that we can visually depict this is to see that when the particle has no momentum but has some position, the rate of change of the momentum is maximal and in the following direction. And if we follow these equations around and sort of plot this as, if you want, almost a vector field, all the particle does is rotate in a circle around and around and around. And this is the oscillation of in both position and momentum. So keep this picture in mind as we move forward, because this picture can then introduce the notion that we can think of the position of the particle in a radial system rather than a Cartesian system. So we can think of the particle as having a position in the x direction, denoted here by phi of t, and a position in the y direction, which is going to be in the imaginary part. We're going to use complex numbers now to write down where the position is. So the variable alpha is essentially just going to tell us where is the particle, and the real part of alpha will give us the x position, the horizontal, which will be it's phi of t, and will be proportional to that. And then the imaginary part of this new constant alpha I've introduced will tell us about what the charge is. It will tell us about the y position. The reason we've introduced alpha is because complex numbers are really nice and simple to use to describe circular motion. Essentially, the entire evolution of the particle we can now write down as this, where alpha of t is equal to alpha of 0, the initial condition, times this factor, which is e to the minus I omega naught t. That's going to just implement algebraically the picture of the rotation that we see here on the circle. And the amplitude alpha of 0 is going to set which of these circles, great circles, we live on. You might ask, why have we defined alpha in this way with these prefactors? And that's a very useful judicious choice. It's one that we've taken. That's going to help us now write down the energy as a function of, that's going to help us write down the energy of the system as a function of alpha and its complex conjugate, alpha star, like this. You remember that earlier we saw that Hamiltonian was a function of phi and q, where we had phi squared over 2L plus q squared over 2c. What we've done now is just to take that expression and factorize it using the complex numbers alpha into this expression up here, which is a quadratic expression, and looks like alpha star alpha plus alpha alpha star. the reason we're going to do this and the reason we're introducing this alpha is because alpha is the closest analogy in the classical world. It's the closest analog to the raising and lowering operators in quantum physics, which typically are a little bit mysterious. But the way you can understand and see them here is that they give you the classical trajectory as much as possible using this expression. And we're going to use this heavily as our bridge from the classical now into unveiling of the quantum harmonic oscillator. So far, most of what we said has been in this world of the classical. Now we're going to hop over the barrier by a set of a few simple rules into the world of quantum. And the prescription we're going to use for that is called Dirac's canonical quantization. There's a few subtleties that we're going to glance over because at the end of the day, you can almost use it as a rule of thumb that works like this. For any dynamical degree of freedom, any coordinates in your classical Hamiltonian, you put a little hat on them, and then they become operators, quantum operators, as opposed to classical variables. You notice that the time t has dropped off since we'll operate in the Schrodinger picture. The Hamiltonian h of phi q becomes the quantum Hamiltonian h hat as a function of phi hat q hat. These are the position operators and the quantum operators. If you're more advanced and you've learned in your classical mechanics class about Poisson brackets, the Poisson brackets of classical canonical variables is this, and that will then get transformed into the commutator, which you probably have seen in Quantum 101, that the commutator, which is phi hat q hat minus q hat phi hat, is equal to IH bar times the identity operator. And finally, before I pause for questions, the two complex variables alpha and alpha star that we introduced earlier, their Poisson bracket was equal to this, and in the quantum case, basically alpha goes and becomes a hat, our lowering operator. So I think with that, maybe I'll pause and see if there are any questions so far.
Yes, there is a question. I'll read it out to you. The question is, are there stationary states in the Josephson's junction? If so, how is a particular state selected? Do provide anharmonicity to the oscillator? And could superposition of states in the junction also be used?
Yeah, that's a great question. Thank you. The stationary states are going to look a lot like this pictorially, if you want, in the quantum world, these rings. And in fact, if you look at the sort of quantum depiction of the depiction of a quantum state in the same picture, it looks like little fuzz around each of the rings. The fuzz is associated with this uncertainty of Heisenberg's uncertainty, or the fact that even at a zero energy or at some energy, things are always fluctuating in quantum, right? Position and momentum cannot be determined simultaneously. The Josephson tunnel junction, which will come in a few slides, is going to reshape this picture you see here, the potential, and it will make it such that these levels are going to not be spaced equally in energy. They won't anymore be sort of h bar omega naught over 2 times h bar omega naught n plus 1/2, where n is some integer. They won't be defined like that. There will be more complicated relationships that will make them different. The junction itself, we're going to treat just as a pure inductor, a pure element. So instead of having the energy be phi squared over 2L, we'll see that instead we'll have the energy be cosine of phi. So a fairly different function. But if you wait for just a few slides, we'll do all of that explicitly. So maybe this question is best answered by the rest of the lecture. So thank you. Excellent. Okay, so let's then use this notion. These are the definitions for the quantum commutator and the classical equivalent of that called the Poisson bracket. We don't really need to go into that. If you're feeling slightly lost, it's okay. This is the quote by Albert Einstein that's always kept me going. If I knew what I was doing, it really wouldn't be called research. So it takes some time. So feel free to re-watch this. This is the analogy now between the classical oscillator and the quantum oscillator. On the left-hand side, we had the classical Hamiltonian. On the right-hand side, we have the quantum version of that. You notice that they look almost identical and almost the same. In fact, I think that we are missing a 1/2 here. That's how I know that they should be the same. In the classical picture, we have this notion of alpha, which tells us about the trajectory of the particle on these rings. In the quantum picture, instead, we have this operator called A hat, the lowering operator. The time evolution of these in the Heisenberg picture looks like this. They're just multiplied by a constant factor of e to the I omega naught t. This is true in the quantum case too. So once for the classical oscillator you solve things classically, you can just transcribe that solution over to the quantum world. And similarly, we can finally write down the flux variable. So using this definition of alpha to solve for phi, you notice that the flux variable phi of t is given by some coefficient, h bar z, where z, remember, was the impedance of the resonator, which is the square root of L over C, the inductance over capacitance, times alpha star plus alpha of t. This is totally classical on the left. All that we've done is change the variables. On the right, it has this slightly more interesting notion and form that phi hat, this quantum operator, is equal to a coefficient called phi ZPF. And I'll explain what ZPF stands for and why we use that notion, times A dagger plus A. Similarly, we can do the same thing for charge, solving using alpha for the classical variables alpha star and alpha, and the quantum operator Q that will represent the charge variable. And there's another coefficient called QZPF. These are called ZPF because they represent a very important property, and that's that of the 0-point quantum fluctuations of the oscillator. Maybe it's worth explaining that a little bit more. We said nothing is ever at rest in quantum, and so even when the particle should have zero energy or its lowest energy, the position and momentum, or the flux and charge, are always fluctuating. The size of that fluctuation, the standard deviation of that fluctuation, is precisely this coefficient, phi ZPF. So if you want, in the ground state, the flux that one would measure, or the charge that one would measure of the oscillator, isn't zero, but is given by a distribution, can be any of the values, given by this distribution, which has a width of phi ZPF and has a width of QZPF. These QZPFs and phi ZPFs are going to be super important to determine all the properties of qubits. They're going to drive all the nonlinear couplings, all the anachronicities, as we'll see in a minute. Since we've gone to quantum, it's sometimes very useful to use matrix notation instead of operators. So in terms of operators, what does the A operator do? Well, A acted on 0, kills the state, it gives just pure 0. A acted on the 1 quantum state, the 1 energy level of the 1 energy level of the harmonic oscillator, called the Fock1 state, gives us the 0 state. The complex conjugate of that, the dagger of that, the Hermitian adjoint on 0, takes 0 to 1 and takes 1 to 2 with a certain prefactor. And in general, these operators A and A dagger can be understood as ladder hopping operators that take you from a state 0 to some state 1 or 2 and so on, and take you up or down the ladder by 1 energy level each time. if you take these two expressions now and write them as matrices, which you could use for computer algebra, which is something we use all the time in Qiskit metal, then the two operators take the following form as matrices, written in the computational basis of the energy levels, 0, 1, 2, 3, and so on. 0, 1, 2, and so on. I'm using nice matrix notation here to say that if you apply the state, if this A operator is applied to the state 1, then as the output, you'll get this column and so forth. This is the basis in which the states are written. And the state A dagger A, which tells us about the energy in the systems, if you multiply these two matrices together, is a diagonal matrix with incrementally increasing elements on the diagonal, 1, 2, 3, and so on. What do the wave functions of the harmonic oscillator look like? Well, if we look at the lowest two energy wave functions, the ground state 0 and the excited state 1 of the harmonic oscillator plotted in the flux basis or the position basis, we'll see that they are distributions over the position coordinate phi. You see, normally a classical particle can never be found in this shaded gray region. However, because we're in quantum mechanics, the particle can more or less, if you want, tunnel beyond its potential well and spend some time where it shouldn't. So the ground state has this distribution that looks like this and has a width of phi ZPF. And the one excited state has one node and so forth. These are the wave functions of the harmonic oscillator when you zoom out and look at not just the 0 and 1 states, but also the 2, 3, 4, and so forth. So if you've taken Quantum Mechanics 101, this is quite familiar. And if it is, then I challenge you to take a screenshot of this and try to answer the following question. Can this quantity be imaginary or negative? See if you can type it in the chat as well. If you're feeling like you want to get some very advanced questions, I strongly encourage you to do these. These are really good for anyone who wants to become an expert in the field. I'll ping me on Twitter, or I'll try to post the answer to these in a blog post sometime soon. But these are a little more challenging. So this concludes our review of the harmonic oscillator, where we took the analogy from classical to quantum. We looked at its energy potential landscape. We understood its Hamiltonian as a set of wave functions, as it's Hamiltonian in terms of a simple function that's harmonic. So the spacing between all the levels is equal, just goes like n. And the eigenstates we denote by this symbol here. A very important notion we found out was that of the 0-point quantum fluctuations of the flux and charge, which are explicitly given by the impedance of the oscillator called Z0. And the fluctuations give you this variance here of the flux in the ground state, and they obey Heisenberg's uncertainty relationship. So the amount of uncertainty in flux times the amount of uncertainty in charge is exactly equal to h bar over 2. Now, almost everything you see on this slide, by a slight tweak, is going to give us the transmon qubit, this bread and butter, the workhorse of the whole field. So let's see how that works. Let's return to the picture of the device here, which looks like this. We're going to replace that element in the middle, not with an inductor, but with a Josephson tunnel junction depicted here. This is an SEM image from a friend of mine. And we see that there are two metal islands. Here's one metal island, which is about 120 nanometers across. And there's another metal island on the top. These are two separate pieces of metal separated by an oxide barrier here in the middle between the two. But it doesn't matter what the microscopics look like. We can always write this down as the Josephson junction tunnel element that looks something like this. And we just care about the amount of flux denoted by phi here between the two terminals, independent of the details. the energy of this potential, the potential energy of this, or really just the energy of this junction, is given by E sub j of phi sub j. The j just denotes that it's a Josephson junction. It's given by some energy Ej, which depends on the overlap area between the two junctions. This is where one island sits on top of the other, and has this function node form of the cosine of the flux across the terminals divided by the reduced flux quantum, which is Planck's constant divided by 2 times the electron charge. One important notion is that we can always partition this energy into 2 pieces, a linear piece and a nonlinear piece, expanding the cosine potential. The linear piece, if you use the Taylor series of cosine of x is 1 minus x squared over 2, ... You find out that the lowest harmonic term, the energy, is this, and the first term that's higher than this, which is anharmonic, has this potential form. It's Ej over 24 times the flux of the junction to the 4th power, normalized in the right units. And schematically, we sometimes write this simply as the linear inductor, which corresponds to this linear form, times the nonlinear inductor called the spider element, which is then given by this expression here. So let's essentially now follow our recipe of the harmonic oscillator, simply replacing the junction by, simply replacing the inductor part by this cosine potential, where we've dropped here the constant term. Instead of the earlier quadratic, we now have this cosine. The particle classically can never be inside of this shaded gray region. The harmonic approximation that we saw was given by this quadratic, which we saw earlier for the harmonic oscillator. And you'll see that the gray curve and this teal curve or this purple curve, they're not very far apart. They're actually quite similar to first order. They're quite related. The relationship for the effective inductance of this, the relationship for the effective inductance, basically the L sub j, the inductance that we can, to lowest order, think of the junction as, which will give us this quadratic purple curve, is given by Ej divided by phi naught squared, the whole thing inverse. How do I know that that's what the inductance looks like? Well, if I go back to the previous slide and we look at this term here, you'll notice that this looks almost the same as the inductance of a junction, the energy of a junction, which is phi squared over 2L. And so you can use the equivalence between the green box and this term here in order to obtain this relationship. And I don't know why it's zooming all the time. Great. So the purple curve here is given by this expression. That's going to be quite helpful because we'll see in a minute. How we can use that to solve the transmon qubits to first order. But before that, let's put some intuition to our discussion. There was a question earlier that talked about how the junction modifies things. The plot that you saw earlier of the circles has now been changed by the presence of this nonlinearity into ellipses. We can no longer have these perfect circles. You see that what used to be a circle now looks more like an ellipse. And in fact, the higher in energy you climb, which gives you these different parts of the terrain here, the shape gets weirder and weirder and more oval and much more different, until at some point you can actually have the particle become free. We won't discuss that. So this potential energy landscape is just given by the following. It's given by the following expression. This is the energy of the classical particle. And so in this case, rather than the qubit or the junction going along a circle, it's now going to go along this ellipse. but each of the different orbits has quite a different trajectory. The ellipses deform as you go to higher energy, and that's because of this cosine potential, which becomes less and less stiff as you go to higher and higher energy. The hill gets less and less steep until at the very top of the hill, you can actually roll back down the hill. Let's walk through the steps to analyze this in the quantum case. So putting hats on everything of the Hamiltonian, we see that we have the potential energy term, just like the harmonic oscillator, charge squared over 2 times the capacitance. Now, instead of having phi hat squared over 2L, we have minus EJ cosine of phi hat over phi naught. We're going to Taylor expand that to lowest order in order to obtain the following terms. This is to the lowest 2 terms, keeping the lowest 2 terms in the cosine and the Taylor series. We'll get the quadratic and the anharmonic term, which is the phi to the 4th term. Notice that the first 2 terms look just like the harmonic oscillator, with no difference so far at all. The only new piece that you haven't seen so far is this extra quartic term. Let's substitute our knowledge. So on the left-hand side, we already worked out in the first half of the lecture in some great detail that we can always write this down as A dagger A. That's the energy of the harmonic oscillator. No news there. This should look identically the same. We're copying and pasting the results from a few slides earlier. However, now we have this term. And if you remember, we used the idea that phi hat was equal to some phi ZPF A dagger plus A, substituting that in here and defining lowercase phi ZPF as uppercase phi ZPF, the coefficient in that expression, just normalized by this constant, the reduced flux quantum, which you see at the very top here, we obtain the following absolutely key expression. If you expand that expression out, you find out that it will give rise to a bunch of terms, which are written out explicitly here. There's 3. There's a number of terms that are quadratic, so things like A squared, A dagger squared. We've used the commutation relations to normal order this, and then a number of quartic terms that have 4 powers of A. So A to the 4th, A dagger, A cubed, and so on. This is where we lean on our intuition. Remember, we said that each of these particles, each of these trajectories oscillate, the circles or the ellipses. And the A describes how they oscillate. The A is associated with the harmonic oscillator. So it oscillates at the harmonic oscillator frequency, omega naught. Well, what that means is that each of these terms in here is one that rotates. And terms like A squared will rotate at a frequency of 2 omega naught. Terms like A dagger squared will rotate at a frequency of negative 2 omega naught. And terms like A dagger A will rotate at omega naught minus omega naught, which is 0. So in fact, they do not rotate. And that's just by taking this. How do I know that? I know that because I've taken this expression and simply substituted it in here. Knowing that some of these terms rotate, we can use a really powerful theorem called the rotating wave approximation, which is equivalent here to first order perturbation theory. If you want, you can just do that, which allows us to first order in approximations, just delete every single term that is rotating, that doesn't have 0 frequency on average. And putting these all together, we'll find the following. Keeping only the terms that we do care about, we find out that to 4th order in the Taylor series and within the rotating wave approximation, the transmon qubit Hamiltonian looks like this. It looks like h bar omega naught minus some coefficient delta q times A dagger A. This is essentially just a simple harmonic oscillator, except that its frequency has been dressed or renormalized by some coefficient that came from the expression above, minus a totally new term that we haven't seen before. And this is the nonlinearity. This is the thing that we have been after this whole time. This coefficient alpha is called the anharmonicity, and this term is nonlinear because you see that we have four raising and lowering operators, something we never saw with the harmonic oscillator. To be explicit, the coefficients are the lamp shift, which has the following form, and the anharmonicity, which in this case happened to be equal, but that's not always the case, which equal just 1/2 EJ squared times the 0-point quantum fluctuations. And remember, we said the 0-point quantum fluctuations will dictate everything. Well, here's our first proof of that. All of the nonlinear effects so far are going to be proportional to the size of these 0-point quantum fluctuations. So the larger these quantum fluctuations of the flux, the stronger the nonlinearity will be. Let's see what the effect of that nonlinearity is. If we rewrite the term a dagger squared, a squared, in terms of the number operator, remember that n hat applied on the eigenstate of the harmonic oscillator n just gives us n times n, and n hat is just equal to a dagger a, then we can write down the Hamiltonian as a linear plus nonlinear piece that looks like this. It's maybe easier to write down the effect of what this rotating of what this Hamiltonian will do. And when you apply it on a harmonic oscillator eigenstate n, then the solutions of the energy levels look like this. We have the usual h bar omega, now qubit, multiplied by n, the energy level, n. However, now there's a correction that depends on n. This is something we did not see with the harmonic case. This is the new part, the nonlinear part. It's called the Kerr-Hamiltonian. And the spacing between the energy levels will now decrease linearly at a level alpha. The way to maybe see this is, let's see if we have the picture here. Yes, here we go. The way to see this is, suppose that I give you some parameters that are realistic for a qubit. It's not too important, but if you like exact experimental numbers, the inductance is 14 nanohenries, the capacitance is 65 femtohenries, the junction energy is 12 gigahertz, the effective charging energy, which is just the electron charge squared over 2 times the capacitance, is 0.3 gigahertz.
I am not the one who is taking the decision. Did you say no?
I think we have somebody unmuted. Thank you. The the qubit frequency will then be 5 gigahertz, and that will be given by the spacing between the lowest level and the first excited level. And here we've shown the wave functions of these. Remember, the width of this is the 0-point quantum fluctuations by ZPF. The spacing between the first level and the second level is now no longer equal to 5 gigahertz, but will be 5 gigahertz minus 0.3 gigahertz, so 4.7 gigahertz. That's given by the anharmonicity. And that I know because we've used the Hamiltonian here on the left in order to look at that. And we will then have the following. We'll see that, first of all, the energy that we find for the qubit is different from that of the harmonic oscillator. That's why I don't write omega 0 here, but omega q, stressed by the nonlinearity. The spacings between the levels are now also shifted, and that's because one way to think of it is that the particle, one, has a softer potential, but two, it can also potentially tunnel, quantum mechanically tunnel through this really tall barrier from this well into the other well. Excellent. And the way that you see this in experiment is that if you were to try to look at the frequency of this qubit, or try to shine light at it at different frequencies, you'll find out that the qubit frequency is omega q, just like a harmonic oscillator. Now, if you look at a harmonic oscillator, you will never see these other peaks, which are spaced out here by an anharmonicity of alpha. So this other peak will appear, which is at omega q minus alpha. The first peak here corresponds to a transition between the 0 level and the 1 level. And this one corresponds to a transition between the 1 level and the 2 level. This one will correspond to a transition between the 2 level and the 3 level, and so forth. Excuse me, keeps jumping. These are the transitions that we see when we think of how the energy levels here will be spaced, going from the 0 to the 1 to the 2 and the 3 and so forth, with omega q here being our qubit frequency and the next transition here being omega q minus alpha. So these are two different ways to show the same thing, either as a transition or in terms of an energy spectrum. If we now use, just like the idea initially with real atoms, the notion that if we use frequencies that only are bounded, to the following part of the spectrum, and we don't want to include that line in there. Let's actually delete that line. There we go. If we only include frequencies in our control that say span and live in this part of the spectrum, we're only ever talking to the 0 level and the 1 level. And that's how we isolate our qubit. So we can, for all practical purposes, throw away the higher levels of the transmon and really restrict our worldview to the lowest two energy levels, to 0 and 1. So we can take the A dagger A term and just truncate our space to the lowest two levels. We can do the same thing with the A operator, throwing away everything else at this point. And if you'd like the more formal mapping, this is how you can relate between the A operator, the N hat operator, and the qubit standard Pauli terms that you might be familiar with, such as the qubit Pauli Z, the qubit Pauli X and Y operators. So this is a nice formal mapping that we won't dwell too much on, but essentially this is how you can now really create a single qubit Hilbert space. All of this is essentially automated all of this is essentially described in a lot more detail with a lot more nuances and more generalized in the following paper. So I can refer you there if you're wanting to get deeper into the physics and details of this. If you want to make this easy and largely just use this in a mostly automated way, Thomas will introduce in the following lecture how to do this with Qiskit metal, with Qiskit quantum device, which you may have at this point downloaded and installed from github.com. I'll only point out that there are a series of tutorials that explain some of these same notions and dive deeper and further as well. So I'll refer you to those videos for more depth and for really using this to now design qubits, as well as I'll note that there's this really nice video and tutorial notebook that will describe all of the steps we just covered with Python source code, and you can plot all the wave functions yourself, and you can vary the parameters and so forth. This is all in Qiskit metal, so I can recommend that for you folks to check out. The links you can take a look at here. Just take a screenshot. The documentation is at the following site. From there, you can find all the videos that are on YouTube. If you actually want to talk and communicate and ask questions and discuss, we use this Slack channel for Qiskit metal, and there we post about weekly or bi-weekly tutorials. So that takes us to the end of the first part of your journey today. We covered the qubit in the cloud, how we realize a qubit from a multi-level quantum system, real physical quantum systems. We then introduced the classical circuit and the LC oscillator. We reviewed a lot of basics and dove very far, very quickly, to then bridge the classical world into the unveiling of the quantum oscillator, which by a small substitution created a land of rich opportunity in the face of the transmon qubit. So what are the next steps? Well, I think the next step is to immediately follow by Dr. Thomas McConkey, who will give us more depth and run real experiments. Check out the problems in this lecture and the device and the extra dangerous bends, and break away from the rules of today. This is Thomas, who's, I think, about to join us here. And I'll just leave you with the final message of a thank you, and keep your curiosity burning. And I hope that if you take one little thing away from today, it will, as long as you took one little thing away from today that helped you comprehend a little part of the mystery of quantum, that today was a good day. I hope you enjoyed that, and we'll take any questions, or we'll let Thomas take over.
Thank you, Zlatko, for such an informative session. I believe that the participants are now well equipped with all the essential concepts that will go into designing a chip. We have a few questions. I'll read them out to you now. The first one is, how the femtofarads are measured from the junction. Will it not affect the state?
Yeah, that is a very good question, because essentially Thomas will cover that in his lecture. So if you really want to know the answer, I'm gonna really put a few arrows here to Thomas. You should ask Thomas. Qiskit metal does that for you, but it's based on the geometry of the device, like how far the pads are. This is a hard question to solve in general, but we've tried to make that as easy as possible, leveraging classical technology. And it will affect all of the parameters of the qubit. So if I go to the earlier slide, here, let's do it actually on this slide. I talked about the 0-point quantum fluctuations a lot, the width of this wave function essentially at the bottom. That capacitance, those how many femtofarads you have, that's going to help determine that 0-point quantum fluctuation.
Thank you. There's another question. When ignoring the higher states, like in Rabi oscillation, isn't there still some probability that the state can leak into higher levels? The second part of the question is the probability negligibly low, or is there some other mechanism to prevent it?
Yeah, that's a great question. Yes, I totally glanced over that. So of course, as you see in these pictures here, we have higher states. And one of the things that a real experimentalist has to worry a lot about is, how good is my approximation? I get, as a theory lecturer here, I get to just make the approximation, but in practice, you have to quite meticulously worry about just how accurate that is. And it depends again on the 0-point quantum fluctuations. If you make your 0-point quantum fluctuation very large, that will make your anchromonicity alpha, that difference in the spacing between the 0, 1 and the 1, 2, very, very different. And the larger alpha is, sort of the better that approximation is, because you're more and more off resonant from driving that second level. You can check with simulations. So I think Qiskit metal will have, once you have the Hamiltonian, you can run like a Q-tip simulation and see what the probability is. Typically it's, sub 1%. But it's a design choice. If you make your 0-point quantum fluctuations not large enough and your alpha anchromonicity is not big enough, it could be 5-10% more. If you make alpha 0, then if you have no nonlinearity, then yeah, basically with unit probability, you'll go up the ladder.
We'll take just one last question before we move on to the next session, which is, what's the power draw like for one of the IBM quantum systems, including and excluding the cooling?
Well, good question. Excluding the cooling, let's see if I have let's do this. So excluding the cooling, there's a very interesting fact here. If we go back to, let's see how easily we can scroll back. If I go back to the numbers that I showed us earlier here, this is actually a qubit that I measured and designed myself here. These are the numbers for that exact qubit. So this is a real device. 14 nanohenries, 65 femtofarads, these are the energies. If you look at the size of those 0-point quantum fluctuations, the flux in units of this reduced flux quantum, that's sort of a universal constant to relate to, is about 0.5. And in terms of number of Cooper pairs, the charge, it's 1. It happens. So basically, one Cooper pair is 2 electrons. So the amount of charge you need to move on the transmon qubit when in the 0 state, that's how much charge is moving. It's 2 electrons. Literally, it's just 2 electrons moving across that junction. So it's minute. I mean, 2 electrons is nothing, right? If you want to go in the 1 state, it's like 3 electrons or something, right? So it's very, very small. And of course, these are superconductors. So at the superconducting level, there's no dissipation, up to some imperfections. So the power there is minimal to 0. Now, to cool that whole machine, to actually control it from the electronics at room temperature, usually there's a number of thermalization stages that you saw in the golden chandelier, so that can be watts, because much of that power is then killed off at the different stages for thermalization reasons. So we can have watts. The cooling power of the fridge, you're going up into high watts. I don't know if we're quoting the exact numbers. I don't know if I remember them off the top of my head, but it's a sizable amount. It's maybe a couple of home fridges.
All right. Thank you so much, Zlatko, for your session and for answering the questions. I think there are a few more questions in the chat, but we'll have to move on to the next session. And thank you once again.
Yeah, thank you very much. It was a real pleasure. And Thomas, it's good to see you. Take care.
So moving on to our next session, I do believe that all of you must be wondering by now that who is Thomas, and he's going to take our session on the Qiskit metal. So I'll take a moment to introduce him. And meanwhile, I'll drop a link in the chat where you can download and install Qiskit metal if you haven't done it by now, so that you are able to engage in this tutorial on Qiskit metal. Please welcome Dr. Thomas McConkey. He is a microwave design engineer at IBM Quantum. He studies extensible architectures from superconducting quantum computing. Dr. McConkey received his bachelor in electrical engineering from University of Ontario and his PhD from University of Waterloo in quantum computing. Today, he will conduct a hands-on tutorial on designing a 2-qubit chip using Qiskit metal. Please welcome him. Thank you, Thomas, for joining.
Oh, thank you for having me, and thank you for the nice introduction. Certainly, good evening, or good morning, or good afternoon, depending what time zone everyone happens to be in. To everyone, thank you, everyone, for your interest in Qiskit metal. It's been a very exciting time with this launch and the growing interest in our community. So we're certainly happy to help people interested in using it get their hands on it, give some tutorials, get people a chance to start trying to design your own qubit chips. So first off, I wanted to do a little, let me share my screen, just review on mostly what Zlatko's already covered. This is all material that he went into far more depth than I plan to, as we're going to spend most of our time focused on how to use metal. But first, I did want to touch base on all the people currently involved on Qiskit metal, and this is still growing. This started, this started off from when Zlatko was finishing up his PhD in Yale, working on EPR, and kind of rolled into this program called Qiskit metal that I started working with him on when I joined just a couple years ago at IBM. And since then, it's been growing in interest, and we've got a much bigger group of people working on it, as you can see on the screen here. And really, the success and growth of it comes down to all these people that spend huge amounts of time and coding working on the Qiskit Metal GitHub repo, which I believe has been shared in the chat. So really, I have to constantly give my praise to all these people working very hard on it. So as Zlatko pointed out previously, for documentation and the other tutorial videos in Slack, you can get to these to find out more, get the GitHub repo yourself, or just ask questions in the Slack. So the plan today is we're going to run through a somewhat live demo of designing a 3-qubit chip. So we're going to just jump right into a Jupyter Notebook, where we're going to design a 3-qubit chip as if it was something we wanted to actually design, fabricate, and put in a fridge in order to measure and do some experiments with. We'll have a list of specific quantum design parameters that we will be aiming to achieve, and we will tune or simulate, analyze, and tune our circuit layout to hit those parameters via a combination of approaches, such as the classical circuit extraction with ANSYS Q3D, coupled with the quantum analysis of the lumped oscillator model, or doing the eigenmode simulations in ANSYS HFSS, and using the energy participation ratio. Now, I know Zlatko already touched on some of the circuit QED aspects, but I wanted to, again, this is very quick. Just, I know I'm throwing a bunch of equations. It's mainly just to show the basic structures and how these relate to our layouts, which we'll be generating inside of Qiskit Metal. So when we talk about transmission lines, this is the circuit equivalent you can see on the screen. These are, if you're unfamiliar, this is the telegraph formula formation of the transmission line, where we're taking the lumped circuit equivalents of that transmission line, and we can use that to determine the characteristic impedance of that transmission line. Generally, you aim for about 50 ohms. Now, that's, of course, the idealized circuit approach. When you're actually doing the layout, as you can see in that top figure on the screen here, your geometries don't immediately relate to, you can't just look at geometry and be like, oh, it's this impedance. You have to actually analyze or simulate it to figure that out. And the image on the screen is an example of a coplanar waveguide. That is what we commonly use, not exclusively. Different groups will maybe use other types of microwave transmission lines, but generally it's a coplanar waveguide. Now, if you're unfamiliar, this basically is a microwave transmission line where your ground plane is a thin film on top of, say, a dielectric, and the center transmission line of that transmission line, that center conductor you can see running through the middle, is what's your trace or signal line, and your microwave signal is propagating along that waveguide. Now, if we have that length of transmission line and add some boundary conditions to either end, as you can kind of see in the bottom right image, we can actually convert that into a distributed resonator, or like a just planar cavity. And that's what allows us to create some microwave resonators. These are very important in any qubit circuit design, as you end up using resonators for many aspects of your chip. Another aspect that's very important is what's the actual quality factor of that resonator. Now, when we can pretend if we have a superconducting resonator, we'll hand wavy ignore many aspects of loss. Even when you have a superconductor at low temperatures, there's still lots of sources of potential loss, but we can pretend the internal quality factor, when it's isolated, decoupled, we can pretend it's infinity. As soon as you couple it, though, that's, of course, a channel for the energy of that resonator to leak out. And that's going to also impact that quality factor. Now, that's not necessarily a bad thing because you need to be able to actually see and measure that resonator, as you'll see in a couple slides. So you modify that coupling strength, in our case, largely by capacitive coupling, as you can see in that zoomed in portion on the bottom right. And by changing that strength of that capacitance, you're able to modify that coupled or external quality factor of your resonator. Now jumping to the superconducting qubit, as Zlatko already did a very in-depth analysis, I just want to point to a couple specific values in your Hamiltonian and the solutions of that transmon Hamiltonian. You can have the full solution, as you see on the top left, but the specific parts I want to focus on is the charging energy, that EC, you can see is primarily driven by the sum of the capacitance seen across your junction. So that's not just your junction capacitance, but the summation of all the parallel capacitance as well. So your junction capacitance, hand wavy, say 2 femtofarad. But when you're dealing with a transmon, the summation of all the parallel capacitance will be orders of magnitude higher. So that becomes much more dominating. And that's how you end up doing a lot of your design and tuning for your, say, qubits and harmonicity, as that's directly tied to the EC, as you can see the circle on the bottom right, where if we're looking at the energy between your ground and excited state, it's roughly equivalent to the square root 8 times charging and Josephson energy. So you're charging energy and balancing these EJ and ECs to hit your target values. Now, of course, your qubit isn't the only thing you're putting on the chip. As I mentioned, it's going to be coupled to resonators, and that's where you can describe the system via your James-Cummings model. Now, don't need to worry about that full Hamiltonian equation. And the main thing, again, I want to focus on is this G value, because that G value is really what's the strength of the coupling between your qubit of interest and your resonator of interest. And that, in our scenario, is going to be primarily determined by the capacitive coupling. That'll come up more again later, but I just wanted to make reference to that. So when I start mentioning things like the G value, you have something to look back on and have some reference on what I'm bringing up. Furthermore, when you're actually looking at, say, the readout, say you're doing specifically a dispersive measurement of your qubit. So you're having a qubit, a readout resonator, such as the bottom left figure on the screen there. And if you're in that dispersive regime, so that the separation between your qubit frequency and your resonator frequency is much greater than that coupling strength between your qubit and your resonator, you can be in that dispersive regime such that when the state of your qubit changes, say goes from 0 to a 1, you're able to have a shift of the measured resonator frequency. Now, this is important because that's what we can measure when we're actually wanting to measure our qubit state. We don't need to directly measure the qubit. We just measure the resonator to see how much has that shifted. And that shift will be determined by chi, this chi value here in the formula of which you can see on the bottom right. And again, there's that G popping up. And as I said, that G is largely, primarily determined in our scenarios by the capacitive coupling. So we're able to tune these coupling strengths just by looking at the capacitance. And that can determine both the coupling strength, say, to our bus resonators between qubits, as well as our readout resonators to set our chi value. So I know that was a whole lot thrown very quickly, but I wanted to just touch base on those values so that when I bring up the design parameters that we're aiming for, we're able to look back and think that's what that value actually means. Before I jump into the notebook, was there any questions from those very quick slides?
I don't think there are any questions right now, so
Okay.
we can continue.
Oh, brilliant. That's great. That means we have more time to hopefully get through the rest of the tutorial. So speaking of, let's go ahead and jump right in. So this is going to be, as I said, a pseudo live demo. I've kind of cheated a little bit and ran simulations beforehand because although I'm sure we love each other's company, probably don't want to sit here for about 20 minutes as a microwave simulation is running in the background and we're just waiting for it to complete. So I have those simulations portions already completed, but for all the rest of it, we're going to just go through as if we were, again, designing a qubit chip from scratch. Furthermore, this might be hopefully no bugs, no errors, no issues. Metal is still in development. It's in a sort of alpha beta state. And I'm actually using one of our development branches because we are refactoring the analysis renderer setup of metal. What I mean by that is previously we had it such that you would need to manually render, and when I say render, I mean take your metal design and put it in a classical software simulation of your choice, say in ANSYS Q3D or ANSYS HFSS, and then run the simulation and separately do the quantum analysis. So we have now created, or we're in the process of refactoring that so that that's all compiled into one step so that you can do all of that in just about 3 lines of code. If you're fine with the default values, you could even do it in 2, but I definitely would suggest always modify your options for your simulations and analysis to better match what you're trying to actually simulate and design. So again, should be fine, but there could be the odd bug popping up. But getting started, I've got this notebook open. I already set up my Qiskit Metal. This is all installed. You can see on the top right, I'm running off a kernel that I have set up specifically for running Metal. So I'm just going to go ahead, import Metal and some relevant classes. There we go. So as I said, we will create a 3-qubit chip. That's our goal. We will have some buses, we'll have some readout resonators, and those 3 transport pockets. So when you go about designing a chip yourself, there's no set rule or structure you really need to follow. You maybe say, pick a qubit and fully analyze and tune it, and then do another part of your layout. Or what I'm going to follow in this case, we'll just design the full layout first. So we'll generate all our components, guess roughly at what the options and design parameters need to be for hitting our quantum design parameters. And from that, once we have our layout fully generated, we'll then go ahead and start the actual simulation and analysis to try to start tuning our layout to hit our target parameters. So first off, I'm going to import the components I'm wanting to use for this design. So I'm going to use a transport pocket with a potential 6 connection pads. Not going to use all 6, but it gives us that option. A few different types of route meanders. So these are really just, these are transmission lines set for coplanar waveguides. Route meander is the form of the class which will auto meander. I think Zlatko mentioned that already about the meandering, and often when we're doing resonators, we have them purposely meander to keep the amount of, landscape that they're eating up of the chip. Pathfinder is an auto pathfinding form of the class, so that you just give a start and endpoint and it figures out how to actually draw between those two. Route straight, literally what the name says, it just draws a straight CPW between 2 points. We, of course, then also still, as I said previously, need some capacitive coupling. So we'll have both an interdigitated capacitor as well as an interdigitated capacitor that's part of a CPWT structure. And finally, just some wire bond pads for the edges of our chip. As often when you are making these chips, you're then putting them into some microwave package and then wire bonding from your package to your qubit chip. And then your package has, coaxial or like PNAs, some connection that goes from it to the rest of your fridge via cabling to your outside equipment. So I'll go ahead and import those and also then create a design and launch the GUI connected to that design. And you can see here the GUI window. Of course, I've not added any components yet, so it's all very basic. I could go about doing some layout from this window directly, but I already have everything coded up. Personally, I prefer writing out my design in code as I find it easier to modify and keep track of everything I've gone up to. I have a nice listing of what I had done previously, but it's really user preference. So from that point, we will also enable overwrite because by default, overwriting is not enabled. So if you try to, say, add a component with the same component name, Metal will stop you. That can be a good thing because you don't want to have done a full design and then accidentally erase something you just did. But since we're going to be making changes very common and going back and forth, I'm just going to enable that to true. And we can also take a quick look to see the options attached to our design planar setup. Default is a silicon dielectric. That's fine. Centered, the sizes, the width or height of your substrate, and a rough estimate of the vacuum gap in your microwave package. Now, I don't think I need a chip this big, so I'll go ahead and shrink mine down a little bit to just a 6x6. Still probably overkill, but hey, it's always nice to have more space to work with. So starting off, we're going to start adding some qubits. Now, as I said, we'll have some particular design parameters in mind. Now, for our qubits, let's say that we will aim for frequencies of about 4.8, 5, and 5.2 gigahertz. And we'll try and have an anharmonicity of all three of about 300 megahertz. Now, we won't necessarily hit those values exactly. Even in the best case, you can often be plus or minus a little bit. But that can be a good target for us to reach for this tutorial. As I mentioned, that G, that coupling strength, that will be largely determined by the capacitive coupling between those center charge islands that Zlatko was showing in his lecture and the connection pads. And we'll aim to have a G of about 80 megahertz for those. And for the readout resonator, we'll aim to have a chi of about 1 megahertz. These are just arbitrary values. They're not necessarily good. They're not necessarily bad. They're just something for us to aim for. So we have a target for this tutorial. Now, we can see all the options that the transpond pocket has attached to it. So these are a combination of the default options, which the component designer, so the person that wrote up that code in Python for this component, for the transpond pocket 6. And you can think of that really for anyone familiar with, say, GDS or other EDA CAD tools, think of it like a super P cell. That's practically what a Q components Python file looks like. So these default options are giving all the values that the front-end user is able to modify to change the structure and the design of their qubit, or of their component, in this case, a qubit. You can see we can change the connection pads, the widths, the heights, where the connection pad is located on the actual transpond pocket. We can change aspects such as the and what will come up often is the pad gap, so the distance between the charge islands of that qubit, as well as renderer options. So these bottom options here, these are not attached at all to that super PCell, that Q component Python file I mentioned. You can open up the Python file. You will not see these anywhere in the code. The component designer is completely ignorant of the renderer options, and that's on purpose. And that's part of, that's a design choice we did purposefully, because we wanted it so that new renderers can be added to Qiskit Metal without needing to go back and rewrite how many potential components are in the database at that point. When a component is first imported, all the renderers that are present in your installation of Qiskit Metal inform what component options that renderer has in addition to the default options for that component. So I have ANSYS renderer and GDS renderer on my Metal installation currently. So we can see things like, okay, there's an HFSS wire bond. So making that true, auto adds wire bonds when simulating in HFSS to any path geometries of your component. There's HFSS inductance. So when you're doing certain simulations, it'll use that inductance value in this replacement of your Josephson junction. So that, say, you have a sheet inductance. I'll get into that in a bit more detail later. But all these default options are there in order to enable that component to grow and have full functionality and variability for the front-end user without needing to do any of that recoding of your component. So these three qubits I mentioned, I'm going to generate 3 using that transpond pocket 6. Changing some of the options because, you know, I don't want them writing over top of each other. I'm placing them on the chip where I think they'd be a good spot, changing the widths and the pocket heights a little bit, giving just an initial kind of guesstimate of what the inductance should be. Also here you can see the cell name, this GDS cell name, that specifically is for the junction portion of any of the qubits. The junctions specifically have a variable representation depending on how they are being implemented. Now, what I mean by that is, so in Qiskit Metal, they just get drawn as a rectangle just to represent where the junction portion of your qubit is. If you render your qubit then, say, into ANSYS Q3D, well, Q3D is just a capacitance extractor, so it doesn't need the junction necessarily rendered there. So the junction doesn't get rendered at all. If you're doing an eigenmode simulation, it gets rendered in as a sheet inductance, where the sheet inductance is set to that 14 nanohenries. When you render or export to GDS, it uses this cell name and a file pointer in your GDS, which I'll get to later, to actually generate the E-beam layout of your qubit to the GDS output. So that variable representation of the junction is what enables a very smooth and easy transition to the different environments that you might want your chip design layout placed into, be it for simulation or your actual GDS output for fabrication. So I then will just create those 3 qubits, rebuild an auto scale so that we can then see them here in the GUI. We see I've done just 1 connection pad for readout, and then 2 buses for each one. And I've changed the bus names to represent in each scenario where those are connecting to. These arrows are the pins of that component. Now, these pins become very important when we start adding buses or transmission lines to our design, because these pins are what enable a lot of the auto generation of the transmission lines. We can simply give where's the start point via the pin, component and pin name? Where's the end point via, again, by the component and pin name? Speaking of, we can jump right to the buses now. Now, when you're making these buses, as I had said, they are resonant structures. They don't have to be but they can be resonant structures. So we can say, determine based on the target frequencies that we're interested in, make some ballpark estimates of what frequency or what the length of that transmission line should be to hit the target frequencies. So with that resonator or guided wavelength, we can use that function. If we want, we can take a quick look to see what's involved with that method. But really, all we're wanting to do is get what is the value of the total length we want to give to the class route meander to hit that target frequency. Now, as I said, the pins are important. That's what's enabling us to do that auto generation. So we can either go ahead and look in our GUI to get the component and pin names, or if we're wanting, we can just look at the pin dictionary, attach that component to see what the pin names actually are. So we'll find those pin names. We can find what the resonator length should be for our, say, frequency of interest for this bus. Now, can anyone think what might be wrong with this length that I'm getting from this function here? Considering what this resulting structure in here, I'll add the component quick so we can see it visually in the GUI. You can see I've added the pins. I just add a little bit of forced length that's to be straight, some asymmetry, some fillet values, and that total length. You'll also see I, in this case, set the wire bonds to true. But we can see in the component here, we now have this nice meandered CPW transmission line. But you can see the component is from here to here. Now, what could be wrong by the total length that I put into this component for that frequency? If not sure, that's totally okay. What is being missed is the fact that that value, that length that I'm calculating, is an idealized isolated value. As soon as you couple, and if you recall from one of those PowerPoint slides, once you couple, the actual frequency changes. You've modified your boundary condition of your resonator. So not only do I have this little bit of extra length of my transmission line because of the portion inside the qubit, but by being coupled, it's now caused a lengthening of the electrical length of your transmission line. Your boundary condition is no longer a solid wall, but like a wheat, and like you have that capacitive portion on either end. So the actual length that we'll find later will be shorter. Now that's okay because we can do that via simulation tuning. We can find that. Using this guided wavelength for an initial estimate tells us is when we're figuring out the placements of everything, like making sure we don't overlap or have transmission lines drawing on top of each other. Since we're using a length that is too long, when we shrink it, we know we'll still be okay in our layout. So after that, we'll go ahead and add 2 more of those buses. You can see now we've added those buses, so each qubit is coupled to each other. But you can see these are not really great looking buses. Like one's almost drawing through the dielectric gap area of the trans-1 pocket. We have little extra curves that kind of don't seem super necessary. So we can then just do some modifications. We can modify that lead-in length, as I was mentioning, that start and straight. We can change the asymmetry, so we can shift that meander portion up or down or left and right. we can add some jogs, which are basically hard coding some initial turns of our meandered transmission line. Again, these are not required. These are really more to have a clean microwave signal layout to your circuitry, because you don't want things too close to each other because you could risk crosstalk. You definitely don't want things colliding, because that'll definitely be bad crosstalk. So having previously, I already went through and made some minor tweaks, figuring out what helps the layout structure look a bit better. See a few jogs here, modifying the asymmetry and some of the straight lead portions. So by making those changes, we can see then now we have a very nice and clean structured layout, very nice and compact. Things are spaced reasonably well apart, so we're not as worried about crosstalk. And we still are meeting the length requirements that we inputted initially, and even though those will change later, as I had mentioned. From there, we're then also looking at the readout and control lines for your qubits. So in this scenario, we'll just focus on having one readout for the bottom transpond pocket, which will be a direct coupled readout. For the top two, we'll try doing a multiplex readout. So we will have a transmission line, a through transmission line, and have the readout resonators of the top two qubits coupled to that transmission line. So first, we'll add a few wire bond launch pads for those transmission lines and readout resonators to terminate to. So we can see we've added these just at the edges of our chip so that they would be easy to wire bond to later. Going to then add some of those capacitive couplers, such as those interdigitated T structures I mentioned previously. For those, we could say aim for an external quality factor of say 2000 for those readout resonators. Again, it's just what value you set for those is going to be very determined based on what kind of experiment you are aiming for, how fast you want your readout to be versus how well protected you want your qubits to be from external noise. So you can see I have those placed now in for the direct readout of the bottom qubit and for that through transmission line at the top. Now for the readout resonators, we'll aim for having them be about 1 gigahertz above the bus resonators, so that there's very little risk of crosstalk. So say 6.8, 7, and 7.2 gigahertz. So again, we'll do an initial estimate of what that length needs to be for those resonators, and the actual instance of the resonators will be very similar to what we did for the buses. I already went ahead and did some slight modifications with jogs so that the layout structure looks neat and tidy and things aren't colliding to or anything like that. And then finishing off the readout for just some of the little portions of straights, we have that through transmission line here. We have qubit 0's readout, and qubit 1's readout to this interdigitated T capacitor. And the qubit 2's readout directly coupled with just a little short straight portion of transmission line connecting it to the launcher here. So I think we have successfully generated our chip layout. It's certainly not tuned. We need to do a bunch of simulation and analysis in order to hit the target parameters that we want for our qubit chip, be it decided based on, as I said, what experiment we potentially have in mind. But for an initial layout structure, this is looking pretty good. Now, this in the past would have taken much, much longer. Now, granted, I did some of this offline before I started. This wasn't all written up directly live, but just drawing these kind of structures in a clean and functional way that would also enable you to quickly make modifications so that, when, say, you're doing your tuning, you're doing your analysis and simulations, for you to be able to very quickly change things like your total length that you're wanting this particular resonator to be. That would not have been like a 1 second change. This is all done programmatically. You're all working from options that take input and rebuild very nice and quickly. And you can then do that closed loop of design modification based off simulation and analysis results to hit your actual quantum design parameters in a much quicker and functional manner. Speaking of, the simulation and analysis portion, which really is where the biggest amount of time, when you're even with metal, that's where you end up spending most of your time when you're working on a qubit design. If you want it to be a good qubit design, we could, in theory, just go ahead and send that layout that we've just generated to our clean room, have it fabricated, and just roll the dice and hope we guessed really well. Probably would not be a good experiment, though. Odds are things will not turn out in a way that leads to, say, something worthy of a research paper. So what you want to go through is start looking at the simulation, analysis, and tuning of your qubit chip. Now, before I do jump into this next step, was there any questions about all the layout procedure I went through?
I don't believe there are any questions.
Okay. No. I will take that to mean that I'm explaining things very well, and hopefully not the alternative where everyone is just extremely confused. So as I was saying, with the simulation and analysis, we have largely three, let's call it, say, primary types of components on our qubit chip. We have the qubit. And for the qubit, we're interested in the frequency, the anharmonicity, and the coupling strength of it to our resonators. For the buses, we're interested in the frequency of those buses and the coupling strength between the buses and those qubits. For the readouts, again, we're interested in the frequency, the coupling strength, as well as the coupling strength of the readout resonator to the external lines. So that could be considered as the kappa, or say the Q external of that readout resonators to the transmission line, say. Now, pretty much all the qubit parameters can be initially looked at and tuned just via the lumped oscillator model. And it isn't as accurate of analysis as, say, energy participation ratio, but because it's relying on just circuit extraction, is able to be done much quicker. And so it's definitely the better first pass, that first initial simulation and analysis that you would look at. It's what enables you to save a lot of time in the long run, because you don't want to be, say, trying to tune your whole chip by just one very big EPR simulation and analysis, because that would be extremely time consuming, and that it would just be very inefficient. So the target parameters we're going to focus on for our chip are, as I said, qubit frequencies of 4.8, 5, and 5.2, anharmonicity of 300 megahertz, a qubit to bus G of about 80 megahertz, a qubit to readout chi of about 1 megahertz, a bus frequencies of 5.8, 6, and 6.2 gigahertz, readout frequencies of 6.8, 7, and 7.2, and a readout Q external of about 2000. Now, we definitely don't have time to go through every simulation and analysis, but what we'll try to do is hit a couple key points so that you can see what some important steps are when you're doing your tuning, and also try to show off the different parts to the metal simulation and analysis capabilities. This is also where, as I had mentioned, the changes to the code base for renders and analysis will become most noticeable to anyone that's already been using metal on their own. Excuse me. So first off, we'll focus on a single qubit using the lumped oscillator model. You can get more details on that at the paper here, or also some of the Qiskit Metal YouTube lecture series delves into that more in greater detail. It would be a lecture onto itself to get into the weeds on that topic. But similar to how Zlatko was showing the circuit equivalent extraction and such of the qubit and coupled systems, LOM basically, anyone familiar with nodal analysis, you can think of it very much like that. You're doing that nodal breakdown of your circuit layout, but with the quantum aspects such as your Josephson junction being taken into consideration and how it's impacting those quantum design parameters that we're interested in. So we'll pick qubit 0 for the qubit we'll focus on. All three are practically the same, just with slight differences in the frequency. So we will import an LOM analysis, create an instance of it where we are telling it the renderer we want to use is Q3D. From there, we can check what the simulation setup is for this instance. We can see what the default frequency is. Since we're just doing the qubit extraction, we can have a frequency around the qubit frequency of interest, how many passes we want our finite for our numerical simulation, or like in this case, the circuit extraction in Q3D to run through, what's our convergence value, or what's like the precision we're aiming for in that simulation, and some other parameters that are specific to ANSYS Q3D. We can also then check what's the options currently default option set for the LOM analysis portion of this instance. In this case, we see we have a junction value for that junction inductance of set to 12. You see that it's we have that CJ of 2, so that equivalent or the estimated junction capacitance, what the frequency of our readout resonator is, and what the frequency of our bus resonators are. Now, we know these definitely don't match to what we have in our design, so we want to make the changes to get those to be closer to what we're actually working with for the qubit 0. And we can quickly make those changes and see that they propagate through. Once that's all set, and for our initial simulation, we can just have the default options for the simulation setup. We want to first make sure and determine that this simulation will have good convergence. As if the convergence on the quantum parameters of the analysis, so say the anharmonicity that LOM extracts from the capacitance matrix that Q3D finds for us, if that's not converging well, even if it looks like the classical simulation is converging well, we will need to have higher precision in our classical simulation to make sure our quantum design parameters are converging. Because if they're not converging and we're tuning our design layout, we're not actually tuning anything. We want to make sure we have good convergence before we start making changes. Otherwise, we are just, flailing in the wind. We're not accomplishing anything. Now, the time and memory for the simulation for this one and for all the others will vary a great deal. The size of the model, the degree of precision, the type of simulation. So these are things you want to keep in mind whenever you're starting these types of simulations and analysis. Don't jump to the highest precision and the biggest model right away. Work your way towards that, because otherwise you'll have some 8-hour simulation that in the end tells you, oh no, all your design parameters are wrong. You probably should have started tunings on a smaller, simpler scale first. So always do your coarse, rough simulation and analysis first, then do your fine tuning after. Now, for our simulation, we both will want to specify what to do with any unconnected pins. So what I mean by unconnected pins, because we're only looking at qubit 0, these resonators will not be part of the simulation. So that means these pins here will not be connected to anything. Now we can specify how we want those treated. By default, any unconnected pins are shorted to ground. We can specify that we want them terminated with an open. And we can do that, see here. We simply specify the component, the pin, and make sure it's part of the open terminations list. Speaking of the component, we make sure that that is specified as what the component of interest we're wanting for this simulation and analysis. Now, those, if we didn't want to jump to the GUI, as I said, did previously, we could just look at the pin dictionary. So you have different ways you can run this. You could do run sim and say, just do the capacitors extraction. You could do run LOM, where it just does the LOM analysis from an already ran Q3D simulation, or I could just do it all in one go. So now I'm not going to hit enter because, as I said, that's a simulation that's going to take some time. You know, I could start telling random stories as that simulation runs, but I think we'd all get a little bit bored of that potentially. But we can see here the qubit 0 being generated inside ANSYS Q3D. And then we can check, once it's complete, the convergence plots. Now, that does not look like great convergence to me. We can see that it's starting to get a somewhat consistent slope, that the values are no longer changing, but it's still pretty, that's not great, especially as we want it to be nice and stable before we're confident that the resulting quantum parameters are on target and the actual values we're interested in. So in that scenario, I'm going to make some changes to my simulation setup. I'm going to increase that target precision and the max number of passes. I could then run it again, check the convergence again, and now see that, all right, that is a much better convergence. That value seems fairly consistent. We have a much higher count of tetrahedrons in our simulation for the meshing of our finite element method simulation. So from that, I can be confident, okay, the results I will be looking at have meaning. So first off, say if I want to just look at the capacitance matrix, this is the resulting capacitance matrix of that qubit 0. We can see, say, if we're wanting to just look at, say, the femtofarad values between that bus 01 and the charge islands. You can see we're at about 10 or 9.5 femtofarads between those two. Now, that I could use and then do a bunch of writing on paper or whiteboard to figure out what these values actually mean. But what would be much faster is just have Metal do it for me and have it spit out with these values, what is my resulting qubit frequency and harmonicity, G values between the buses, where the order of these is matching the order of readout bus 01, bus 12, or sorry, bus 02, and your chi. So this being the readout, and then the chi's of your two buses. Now, these are very off what we were aiming for. You know, we're wanting a qubit frequency of 4.8 and harmonicity of about 300, which actually 313 is not too bad, but still, it's not 300. And these G's are very far off from 80 megahertz. Now, what you would then do is make modifications to your layout, say like this, or you could do it from the GUI directly, and make the appropriate modifications for the LJ value, because you're wanting to, as I said, change the anharmonicity. Sorry, is there a question? I'm going to guess that was an accidental unmuting. So making those changes, we can have those propagate through to our layout, and then we could run the same simulation again. After running, we then look at the LOM analysis, and we can see what the resulting values are. So having made those changes, we see now that we have a qubit frequency of 4.78, about 4.8 gigahertz, and harmonicity of almost 300. We can see that we have a G now of close to 80, and that readout chi of about 1 megahertz. So from that, again, as I said, this is for your initial coarse tuning. Those are pretty good values. For fine tuning, you'd want to do, say, your EPR, maybe an impedance simulation. But for an initial first pass, that gives a pretty good like tuning layout, modification of your layout to hit your quantum design parameters. So for that point, you could then jump to the other qubits, do the same simulation analysis in order to tune those to the target parameters. But that's going to be very time consuming, and we're quite low on time. So we would just go ahead and jump to closing that instance of the simulation and moving on now to tuning, say, bus 02. Before I jump to that, was there any questions?
Yes, we have a bunch of questions. I'll read them out to you.
Certainly.
The first one is, a participant wants to know about EMC protection of transmission line coupling the qubits.
Oh, so that's generally any form of that kind of EM protection is really being achieved more through your microwave package. Now there is, say, work done by different groups where actually some interesting papers from Shulkoff groups at Yale. And I swear I'm not just doing that shout out because Lacko's on the call, where they were proposing different types of cavity structures over tops of coupling components to protect against each other. And there's a lot of work going on that, on how to keep as clean an electrical environment on your chip as possible. But the broad course approach is with your initial just microwave packaging of your qubit chip itself.
Thank you. The next question we have, which I understand is more related to post-tuning analysis, is how can we check that we have built the correct code?
For, say, a Q component?
I believe that is when this question was posted.
Okay. Yeah, for a Q component, it's just testing it, making sure that the structure and layout is functional. There's in the Metal GitHub repo, there is some test examples and also simple examples that you can compare against to see, okay, my parameterized layout structure, like my geometries, then things like your generation of your pins for the net list in essence, and then say adding of the Q geometry, which I haven't gone into. That's more of a deeper dive, but that's where it translates the layout structure of your component into the metal geometry database. I hope that answer was able to answer that question.
There's a question following that, which is that does this mean that cross-checking of inputs is needed to have a good result for Q components?
Yes, you definitely would. I would advise always doing that kind of check. Now, there's two ways to think of what would constitute, say, a good Q component. You could have it just from a code base where it's like, okay, is the user's input not causing errors or breaking the code? Is it functioning regardless of making sure that the user's not breaking the design by putting in this component? Versus, is it a good Q component in the sense of for an actual electrical circuit, like an actual part to your quantum chip? And that really would take a lot of, long term would take a lot of simulation analysis and ideally measurement in your fridge to see if it is performing in the manner that you wanted, designed and wanted it to. Because there can always be aspects that you maybe don't initially expect. One thing that comes up a lot is two-level system loss. And that's something you only see when you're at very low power, like at a handful of photons in your cryogenic environment.
Thank you. There's the last question before we can go ahead.
Sure.
It is there any mutual inductance between the inductors? If yes, how does it reflect in the results?
Yes. So there can be, similar to, say, if you have your transmission lines too close to each other that they're capacitively coupled, same can be true. Now, when you're dealing with resonators, what can be handy and nice is for the frequency modes of interest, you'll have voltage and current nodes and antinodes. So you can be a little sneaky with how you design your layout. So say where there is a current antinode, you make sure it is not near any other current antinodes, say. And that's, one way to avoid that accidental mutual inductance. And that's a trick that's been used for both increased coupling or decreased coupling in microwave engineering for decades. And that's honestly true for much of the design and steps we're using in this layout. It is largely microwave engineering. Much of the design ideology that we're going through and like what's a good structure or layout really is just old-fashioned microwave engineering. The quantum elements is really where we get to the more analysis portion, or again, of course, specifically the qubits themselves, but largely it is we're able to just use standard microwave theory.
All right, thank you. Is there room for another question before going on?
Certainly, yes.
Okay.
You tell me when the time's low.
Okay. So the question is, in real-time quantum computation, we face a lot of noise and errors. Does this type of simulation in any manner help us better understand or mitigate or implement error correction or noise reduction?
So it can in a manner. It does not necessarily directly, but it can say that you're suffering noise from your to your qubit due to one of your couplings, and it's resulting in a very low T1 per cell. So then you can aim to, you can look at your simulation results and see, okay, the T1 per cell for this coupler portion is very low. Then okay, I need to weaken that coupling in order to help protect my qubit more. Outside of that, say for error correction, that'd be more a case of, are you making a surface code or something along those lines? And then this would help you design your circuit layout to hit what type of parameters you need for that surface code. But the design, metal itself isn't implementing an error correction.
All right, thank you. You can go ahead.
Cheers. I suspect I won't get through all of this, as, correct me if I'm wrong, I was supposed to end technically a minute ago. How much time do you think would be remaining?
I think we started 15 minutes late, so we can have that much room.
Okay, I'll kind of go through the remainder quickly, because it's sort of doing much of the same that it did previously. But in this scenario, we will look at focusing on bus 02. And for that, we're wanting to just look at the resonant frequency. So we will actually, in this case, import the EPR analysis and create an instance of that with the HFSS renderer chosen. Now, from there, we can again look at the setup of the simulation. What's the, say, number of modes, the precision value, max number of passes, similar to what we did in the LOM. Now, in our case, what we're wanting to really do is we're just trying to tune the frequency of the bus, just to get it to about that target we had of, let's see, bus 02 should be 6 gigahertz. So in that scenario, we want to just do an eigenmode simulation, which is what this EPR analysis will set up for us. But we don't need EPR analysis on it, because we're just, again, we're just extracting the resonance of that bus. We can later on do EPR analysis if we wanted, but for this, it'll be a nice simple simulation. And so we can do a couple checks while doing this as well. First, we'll set the number of modes to 2. Now, this enables us to definitely grab the resonant mode of our bus resonator, but we will also set this box plus buffer to false. Now, what that value does normally is, when rendering to ANSYS or simulation software choice, it won't draw the whole chip, because the whole chip could be quite large. It'd be time consuming to always simulate the large chip, even if you're only looking at, say, a qubit in the middle of it. So default, this is set to true. And so instead of drawing the whole chip, it draws a portion of the chip around the circuit or component of interest. So what we'll do is set this to false so that we can have the full chip. We set the number of modes to 2, so we can check if the chip mode might be a frequency of concern. Now, 6 by 6 millimeters of silicon dielectric, that first the mode of that chip structure is going to be much, much higher. But we'll pretend we don't know that, and we can include that in this one simulation as a sanity check. So we're going to, in this scenario, render bus 02, the component we're focusing on, but we also want the connection pad terminations to that bus, because that is, as I said earlier, a part of the electrical length of that resonant structure. So we need both of those, but we don't care about simulating the qubits themselves in this case, so we're going to turn the junctions of those 2 qubits off. So they're just sitting there as little capacitive islands that are impacting the resonance of our bus resonator. So I could hit enter and run the simulation. Again, I won't, because that'd be time consuming. But having already done that, we can first do a quick check, see if we had good convergence. This is not brilliant convergence. I would definitely expand this to more passes, but we'll just assume that this was a good convergence. Realistically, this probably should go to like 16, 18 passes about. We can then get the frequencies, and we can see even here that these are not quite the values we were aiming for. We can also make sure by plotting the electric fields that that first mode is actually of the resonator. And although this is a sparse mesh because of a quick simulation, you can see the electric field is definitely present around that resonator. We see that like it's not a chip mode, it's not any other structure that's causing that resonance. And you can see here also the auto-generated wire bonds around that bus resonator in order to mitigate slot line modes and things like that during the simulation. So we know that's the wrong frequency. So we would want to modify the total length of bus 02 to get it to the correct frequency. Now, we could just do that simulation each time after changing the total length a bit, or we could take advantage of the sweeping class. Now, the sweeping class in this scenario allows us to take a component or multiple components, sweep a design parameter of interest. In this case, we'll sweep along the total length, run the simulations for each of those lengths, and get the resulting output frequencies so we can see which value is actually the value we need to hit the design parameter of interest. So from here, we would simply set up the design simulation specifications. Again, a slightly increased number of max passes. When doing this sweep, we know the first mode is the resonator, so we can get away with just the first mode, what the precision we need for that, and then we can go ahead and run that sweep. We specify it's for component 02. We're wanting to sweep total length, and we'll pick these values to sweep across. We again specify the components we want to have in the simulation, but we want the junctions turned off. And then from that, again, won't run the simulation because that would take a bit of time. We could find that the resulting values give us that range of what the potential lengths need to be to hit that target frequency of 6 gigahertz. Having done that previously, I can see that it was about 9.4, gives us the correct simulation or correct resonance result, and allows us to finish tuning that bus resonator. Now that would be just one way to quickly do the resonant tuning for your buses and even for your readout resonators. What can become more in-depth and give better final results is if you then include an EPR analysis. Now, the more in-depth review of that in the paper that Zlatko also previously pointed to, it gives a much more fine-tuned result by considering the participation ratio of the fields of particular modes interacting with the different structures of your layout. So in this case, we could say look at qubit 0 and 1 and bus 01 together as a whole, so that we include all 3 modes. So both the bus resonator 01 and the 2 qubits of interest. We can first make the modifications to qubit 1, presuming we did LOM analysis on it already, and also look at bus 1's, presuming we already did that resonance analysis and tuning that we did previously, and make those modifications to our layout. So we already did the coarse tuning to those components previously, or we're going to pretend we did. From there, we can make an instance of the EPR analysis, having already imported it previously. We don't need to again. If we think we're going to be needing to make a lot of fine-tune changes to, say, our qubits junction inductances, we could just go ahead and attach those values to variables, as Metal is supportive of variables, and then specify this simulation setup to, say, be more fine-tuned, because for EPR analysis, you want to make sure you have very good classical convergence in order to be sure that you're getting good quantum analysis results. Now, these results won't be great that I'm about to show you, because honestly, these are not very fine-tuned results. But simulations take a while. So if I make those modifications based on previous tunings of, say, the expected junction inductances, I could then run that simulation, check the convergence. You can see here, these are actually still increasing, so not the best convergence. Also of importance is the fact that you can see these values are a bit higher than they should be. But keep in mind that this is the classical resonant structure. This is not with the anharmonicity included. So these are just the classical eigenmodes. Once we see the EPR analysis, we'll see that the qubit frequencies are more closely matched to what we're after. So assuming these were good convergences, we could continue on and actually set up the EPR analysis. Now, since we have two junctions, we want to get rid of the default setup for just the single qubit junction, and then we'll add the junction design aspects for the two we have in our simulation, the junction for qubit 0 and the junction for qubit 1. Now, these are simply specifying for, to EPR aspects such as, oh, this is the name of the sheet inductance in my EPR analysis simulation. I can show you that over here quickly too. This has already been drawn. So you see here, this sheet inductance has this name, and I'm simply using that to inform to EPR what to look at when it runs the field calculator inside of ANSYS. So once that's all set up, we could then run EPR. Again, a little time consuming, so I won't go through all that. But I did do that previously and took a screenshot. Again, the results are a little iffy because the convergence wasn't great, but it gives you an indication of what the outputs of the EPR analysis would look like. We can see from the matrix on the diagonals, we see the anharmonicities, and the off diagonals are giving us the chi's. So in this case, it's the 2 times chi's. So we can see what the chi, 2 chi to the between the qubit and the bus, and we can also see what's the chi between the 2 qubits. Even though they're not directly connected to each other, their fields are interacting, so that we can see how those would actually be interacting and what that value ends up being. And that enables us another manner to do that tuning. If we have, say, a sense of, we know what coupling strength specifically we want the 2 qubits to have to each other, not too worried about the qubit to the bus, we could tune just based off of that value. So from that matrix, we could make some changes to the bus 01 pad width and the bus 02 pad width. That's a typo in my case. Oh no, sorry, it is the bus 01. It's qubit 0 and qubit 1, not a typo. In order to get the coupling strength that we're specifically aiming for. Once that is all complete, we then could just close that EPR analysis. And assuming that we've finished tuning the entire chip, everything's working brilliantly, we could go ahead and just jump to generate our GDS file of our layout. That's via the GDS render, and you can see a huge selection of GDS render options here. This is still certainly work in progress, but you see everything from the file that is being pointed at in terms of importing of that E-beam layout structure I mentioned for the junctions, or the, say, specifications for the cheesing of your ground plane of your GDS output. So I selected a few just options, changed them up to show how that would look, and then go ahead and I'll just generate that GDS file. And it should be, oh, go ahead and grab this guy over here. And we can see it is the resulting GDS. So this has a few extra layers still because it's still being worked on, prototyping, but practically what you would end up sending to your clean room to fabricate is this guy. We see the layout structure for your lithography. We see these little cheesing holes present throughout the layout. And we see also, although these are not good junction E-beam layouts, certainly, these are just an example. We can see the layout structure of what would be an E-beam pattern for a Josephson junction to be generated by, say, double angle shadow evaporation. And so from that, we have gone from an initial design idea to a fully generated GDS file. We skipped a few steps, maybe cheated a little bit in me having done some simulations previously, but hopefully that's shown that there is a lot of the, say, hardware, like a lot of the headache style and monotonous work that used to be part of designing of these chips has been taken over by metal, so that you get to save a great deal of time and have a cleaner feedback loop to hopefully catch any of those potential errors or issues that come up when you're designing and simulating and tuning your qubit chip. And with that, I'd say thank you all for your attention. And if any further questions, I'm happy to answer them. But as Zlatko also said previously, feel free to join us on the Metal Slack in the Qiskit workspace. There's all those YouTube videos delving into greater depth on all these topics, and tons of documentation to read through if wanting to learn more. And please give the go ahead, grab the repo off the GitHub, give Metal a try. If you like it, try contributing. It's meant to be an open source community. You keep what you make. It's all open source. There's, we claim no ownership for anything that you make. It's completely free, open license. It's hopefully a tool that will grow beyond anything that we imagined and be helpful from academic to industry.
Thank you so much, Thomas. I think after this tutorial, we all can really appreciate the importance of Qiskit Metal as a wonderful tool for better understanding and designing quantum hardware. And there is one question. I think a participant is unable to import EPR analysis, but other than that, he asks if there is any other backend available for EPR analysis other than ANSYS.
Oh, yes. So currently, the only active simulation renderer with Metal so far, this is just current, is ANSYS. We are planning to, and in the works of expanding it to include software such as Keysight with like ADS and EM Pro, or like say Cadence, Sonnet, and honestly, for all that kind of work, if there's a simulation software you really like, talk about it on the Slack. This is stuff where we'd love to see the community also contribute and like trying to make up more renderers, because there's lots of simulation software out there, and it'd be great if we were able to see people adding to that renderer database. For EPR, it is a little bit more restrictive because it needs to use the field calculators, and not much simulation software has that as part of its system. I think some are starting to add eigenmode simulations and like extraction to their software, but to my knowledge, well, you probably could in some manner in COMSOL. I've never tried it, but to my knowledge, it is currently just the ANSYS HFSS that enables that.
Thank you, Thomas, and thank you to all the participants for sticking out here for 3 hours. And thank you for your enthusiasm.
Thomas, lot of work. Truly, we appreciate your contribution to this school. Thanks a lot.
Oh, cheers. No, thank you for having us both. It's a lot of fun and great to see the enthusiasm and excitement for quantum computing in general, honestly.
Yes, thank you. And Subrata, thanks a lot. You have taken a lot of effort. I truly appreciate your effort.
Welcome, sir.
Cheers all.
And it will, yeah.